Hello, everyone. Today, we'll share several insights and real-world cases with my partner, Ruide from ByteDance. And we'll mainly focus on the secure and efficient AI. This work is a result of teamwork between the Intel and ByteDance. So, can you? Sorry. First, my name is Jiao. You can also call me Jenny. I'm an AI framework engineer in Intel, focusing on the area of big data and analytics with AI. I'm the key contributor of BigDL, and also I help customers to build end-to-end AI solutions on big data platform. And Ruide is a security architect in ByteDance. He's focusing on infrastructure security. He leads the landing of confidential computing and zero trust computing in ByteDance. In the first part, I will briefly introduce the background, the pain point, and the solution within Intel with the industry customers. Nowadays, people are becoming more and more concerned about the security and the privacy in AI. However, building the security applications is not easy. In general, there are two ways to build the secure AI applications. One way is to developers and data scientists need to rebuild and redesign the existing applications based on the privacy and security requirement. Another way is they just try to migrate or enhance the existing AI applications. Due to the complexity, due to the complexity of AI ecosystem, rebuilding are far more expensive and time cost than the migration. So this is the main advantage of the trusted execution environment. In trusted execution environment, Intel has accumulated deep expertise for many years. Since the fourth generation of Zhang platforms, we have two kinds of hardware TDX on the Zhang platform. In the early stage, we have SGX, which is a software guarded extension provided by Intel CPUs, focus on the process level protection in applications. The SGX provides the hardware level security and characterized by the high security, a small attack surface, and high performance. However, the disadvantage of SGX is apparent because the users need to rewrite the applications or modules using the SGX SDK. To address this problem, the open source community and Intel has collaborated together to create a middle layer, which is LibOS. The LibOS allows applications to run the SGX directly without any code change. With LibOS, developers don't need to rebuild applications, but they still need to migrate their applications into LibOS. Now, Intel has a new hardware TE, which is TDX. The TDX is the trusted domain extension, which is focused on the securing the entire virtual machine on the cloud or local data center. So we don't need to have change anything in applications at all. We can create trusted VM or containers on cloud or data center. And then the TDX will protect the confidential data model and the applications from the untrusted admin and adversaries. Although we already have the SGX, LibOS, and the TDX, there are still some pain points when we're trying to migrate the real-world AI applications. The first problem is migration overhead. Even we have the TDX and LibOS, we still need to prepare the environment, create the image, enclave and packages, and finish the functionality test. The second problem is enabling secure features. Although many AI frameworks already provide secure features, but we still need to enable these security features based on the AI workloads. Some frameworks may need to do the security patches to fix some missing issues, like the network encryption. And to provide end-to-end security, we also need to enable the remote attestation, add key management, and provide encryption pipelines. Now we already have the applications ready to deploy to the to production, but it's still not easy. In the deployment, we need to also do some things like the optimize performance, integrate with the existing services. So these pain points require a lot of engineering effort and expert knowledge. So that's why we create a BigDL PPM. BigDL PPM is for privacy protection for big data and AI ecosystems. In BigDL PPML, we integrate remote attestation and packages and patch some frameworks and do the crypto I/O and do the network protection, and also do the end-to-end optimizations for detailed AI workloads. With the PPM, customer no need to do. They can focus on their working on the building interesting and useful AI applications. There's no need for them to do the migration, detail security issues, and do the performance optimizations. Because we add the security, so the overhead will be affected. But in BigDL, we provide a convenient way to optimize the end-to-end performance for AI workloads. Actually, for developers, there are several ways to do the AI optimizations, like the OpenVINO, IPEX, AMAX, etc. But the best optimization solution cannot apply for all the platforms, workloads, or models. So to reduce optimization overhead, BigDL introduced the BigDL Nano for AI workloads. Nano will provide automatically optimizations based on the platform models and frameworks. The only thing that users need to do is import Nano and add several lines according to the documentations. And then BigDL Nano will do the rest of the optimizations. So that's the first part of this talk. For the second part, let's welcome Ruide to give an introduction of real-world cases. Thank you.
Thank you, Jenny, for the introduction. And I'm Ruide. I am right now a security architect at ByteDance, and I will use the next few slides to introduce how we build trustworthy AI product for our users, internally and both externally. And our product, the trustworthy AI products are built on top of the technology provided by Jenny's team, the BigDL team. Okay, so the product we are building is called Jeddak Sandbox, and the Intel Intel's BigDL is used inside the Jeddak Sandbox. Jeddak Sandbox is a trusted computing product that is built on top of TE, and it aims to provide users with high security, high availability, and also high performance. So the users of Jeddak Sandbox have a very easy to use UI so that they can perform most of the data analytics they want, and all the complexities, including the remote stations and also like very like pen to the ass features are hidden inside. Furthermore, we integrate a number of frameworks for big data and AI, catering to the diverse user scenarios and requirements. Because of time, I cannot dive into the details of each component, but like if you are interested, I'm totally open to discuss more. So in particular, like as I mentioned before, the technology we depend a lot on is the BigDL. So with the BigDL, we are actually able to enhance the security posture and also to boost the performance of the like various number of like the AI frameworks and big data frameworks we use in our product. So in addition, the BigDL actually provides reference solutions to significantly simplify the deployment process of our product as well. So. Yep. So before, on the slides before, I just showed like the overall architecture of the Jeddak Sandbox. But besides the overall architecture, it actually currently supports a number of AI algorithms, including the neural networks and many other like popular like AI algorithms. So users, they can intuitively configure the parameters through a UI to complete the modeling process. And they can also obtain like real-time evaluation results through the training phase on the platform. So in terms of the performance, the Jeddak Sandbox includes the acceleration features, this is what Jenny just mentioned before. So it's from the BigDL Nano, such as the distribution training, the instruction acceleration, and also the compiler accelerations. So in terms of security, we have also integrated like security protection solutions related to their platform, the BigDL platform, such as the RATLS, which is the remote station TLS, to ensure the confidentiality of the data and models during the training phase. I will not go through all the steps because of time, obviously. But like I'm totally free to open to discuss later. So besides training, we also provide serving in the Jeddak Sandbox. We integrate deep learning frameworks such as TensorFlow serving and Torch serving to achieve security and real-time model inference. Also, Jeddak Sandbox combines optimizations for serving frameworks from the technologies provided by the BigDL Nano team, as well as CPU-accelerated instruction sets such as BF16, IPEX, JIT, and etc. These features actually significantly improve the efficiency of the model prediction. We will actually see later on some slides of the performance results. And at the same time, Jeddak Sandbox has designed mechanisms such as access control and secure channel to protect the data during the inference phase. Yeah, this is a slide I was just mentioning too. So TE has an impact on end-to-end performance, obviously. And in this slide, we show that on the Intel's TE platform, we can observe performance loss of less than 10%. And another important point we want to make here is that the Intel TE is fully compatible with Intel's recent effort on using new CPU hardware features to optimize the AI workloads. And by utilizing the hardware-level instruction sets such as AMX, we can see the performance is improved by 3 times for both the native platform and the TE platforms. This is one of the major advantages of TE. It could take advantage of innovative hardware features seamlessly. So basically, if there is an improvement on the native workload, you can also see there in the TE platform. And in this slide, we take a deeper look on how BigDL optimization helps in our scenario. We use PERT in our product, and PERT is a variant of BERT. From the figure on the left, we have performance data for BERT trained using PyTorch distributed training. You can observe that in the FP32 scenario, native platform performs better than TDX, and TDX in turn performs better than SGX. This is because both TDX and SGX have performance loss due to their design, but TDX have lower performance loss comparing to SGX. And this is because of the enabling of the instruction set acceleration I just mentioned before, such as the BF16 and also the AMX. And the SGX currently, due to incompatible with the IPEX instructions in the libOS, so it has somehow lower performance than the TDX. And we expect that the libOS team will actually solve this issue in the future. And in the model serving scenario, we observe a similar trend, with the only difference being that the AMX optimization on serving brings a 4-time performance improvement. So, yeah. And in the future, for the Jeddak Sandbox product, we plan to improve user experience. We plan to support more algorithms, provide custom modeling scripts, and we plan to improve the debugging capabilities as well. And second, we also want to improve the performance of the training and serving. We would continue to invest in our collaboration with Intel, and we want to integrate more advanced hardware features from Intel. And third, we have plans on exploring the upcoming confidential GPU. Last but not least, we will explore more scenarios, such as exploring the large language model, which is a really hot topic recently. So, yeah, that will be the presentation. And thank you.
Yeah, hi, welcome. I will be talking about writing digital exams and securing them with remote attestation and cloud computing. I'm Tore Sommer. I'm from the University of Applied Sciences and Arts, Northwestern Switzerland. A very long word, normally abbreviated to FANW in German. So a bit about us, because we have probably a different background than most here. We are a multidisciplinary team going from developers, security experts, to normal lecturers in the university, to people that are involved in university development. And what was the goal that we set out to solve? So we wanted to do competency-based digital exams. What does that even mean? So for that, I brought 2 examples. It means that students want to write about the same thing in their exam that they're normally taught also in class. For example, in life sciences, we do a lot of analysis of images, and during the exam, they also want to do that digitally. So they do that with their computer, and they want to do that also during the exam. Another part is from the School of Education. They do a lot of assessments, so speaking, writing, and they want to do that at their own pace, on their own devices, listening to audio files, recording them, and write about that. So which challenges did we face or did we want to solve? First of all, if we want to move to digital exams, they should be still fair. They should be secure in the sense as they are secure as an exam written in a lecture hall. They should be easy to use and robust. The worst thing that can happen during an exam is some technical issue and you cannot write your exam. That is a fear that every student and every lecturer has. So that should be solved. And also, we need to enable the platform to do that, and for that we choose that we want to do bring your own device. So that is also an important part, so how we wanted to solve that. So how did we do that? We have 3 components. First of all, we have LearnStick, which is a Linux distribution that provides the lockdown of the device itself. Then we have Keylime, which is a remote attestation project that we secure the LearnStick environment with. And then we have Campler, which is our management interface to write the actual exams on, which is also running the exam in the cloud, but for that we look at that a little bit later. So I said, like, we want to do bring your own device, but bring your own device. In the normal system, the student brings their own device, as it says, and then you install some software on top of that to write the exam. So our trust boundary is between the application and the operating system level, which is kind of difficult because the student still controls the operating system and we cannot secure that layer. So what we call bring your own hardware in that case is that the student just provides the hardware and we use our own operating system, in this case LearnStick, to secure the operating system level. That has also the advantage that the student doesn't need to install any software before the exam, they just need to boot this distribution. But of course, we still don't have any trust established in the hardware, and then here comes in the remote attestation part, where we use a trusted platform module to attest also the hardware and bind our operating system trust also to the hardware itself. So I talked about a TPM here in the room. Does everybody know what a TPM is? Just show of hands, probably. Yeah, it looks good. Just a small refresher, provides cryptographic functions and also provides us a device identity. And mainly the big part here is that we can have the platform configuration registers where we can chain it to the root of trust of the TPM to secure the operating system that is running on that. So we have now, we now take a look at the cloud assessment management platform, and it's based out of 3 parts. First of all, we have the backend. So we want to write an exam, so it provides all the interfaces, and so it provisions the VM where the exam is actually written on in the cloud, has the security properties, and yeah, provides also some user management and some integrity management of the data. Next, we have the lecture view. So we wanted to make it easy. The lecturers can only create new exams based on templates, so they don't need to know how to configure an entire VM. They can hand in some data where the student can the student can use during the exam, for example, the task or the material that is used during the exam. And then lastly, on the student perspective, we have that they can hand in data, which is important for open book exams. So the student can hand in data beforehand, and then they normally log in to the exam and can write the exam, and afterwards also hand in data. So here, the process is that also the lecturer itself cannot interfere with any of the exam process itself. It can only start, monitor it during the process in the means of is the exam running, and also stopping it. So how does that look in practice? We have our student device. Then we boot from that device. So we have the TPM to ensure that our security, and we boot up, and we have the Linux integrity measurement architecture and secure boot and all that kind of stuff running. And then we connect to the cloud system, and in that system we have now the Keylime component running that is now attesting does the student actually have booted from the right operating system with our security properties, and otherwise also the management system that now provides either like a cloud RDP session, so we run, for example, in Azure Cloud and provision like a new VM for the student there to connect to, or in a very simple case, we can also provision like a web browser session. So if you had e-assessment tests over like an e-learning platform that can run locally for that, you don't need any resources in the cloud. So then the student connects to that and then writes the exam, and afterwards they can hand it in, and that's that. So what are the challenges of actually doing that? First of all, we talked about also today a lot about remote attestation and what data we want to attest. But first of all, collecting the data from the distribution of what data do we want to attest, how do we test it, how do we define a trust opinion, and also defining it in a way where normal users can understand if the system is secure or not. Second, threat modeling is a very, very important thing if we talk about trust, because against what kind of threats do we want to actually protect? in our case, in an exam, in a lecture hall, we want to be as secure as a paper exam. So it's not the magic bullet to solve all your problems for cheating, but it should be as secure as a paper exam if you write that. So that is also important if you communicate to non-technical people what technology can enable you to secure and what not. Then also abstraction and separation. We try to make it as easy as possible for the lecturers and also for the students to use, so that they don't need to care about what is a TPM, what is secure boot, what is the trust decision in the end that's happening, or for the teacher, they want to just write an exam with the right software running and not want to care about what is running actually in the cloud. And lastly, we run on consumer commodity hardware. So we heard a lot about trusted execution environments today, but as of today, the only thing that we have on commodity hardware is integrity measurements with TPMs that are readily available, and also integrating that fully with different hardware manufacturers and seeing that we can run on those. That was a challenge that is solvable, but also very, very hard. But the conclusion is it actually works. We run our Campbell system now over 100 exams, not all of them with like TPM technology enabled, but that works, the base platform works easily. Then we now run on 340 different devices, so from different manufacturers, different notebook manufacturers, it generally works, and also from the students and from the teachers. We have a very high acceptance, which is very good because they want to do competency-based digital exams, because it doesn't make an exam easier, but it makes it way better to apply what they learned from the real world to also to the exams. So what are the next steps that we want to do? So in Linux, we have mandatory access control systems like SE Linux and AppArmor. We want to fully integrate those also locally. There's a lot of challenges of, for example, prohibiting shells and interpreters for users to run. If anybody tried that of you tried that, please get in touch, because it's a difficult problem to actually solve. Then we want to do more. We want to look into confidential VMs, because currently we run our VM in the cloud and provide some guarantee with that the data is in, with the data integrity from our side of the system. So if the student hands in their data, we sign it, we hash it, and provide the student with a hash where they can validate that their submitted data and the data that the lecturer corrected is like the same. But of course, we can now start leveraging the technology to also provide a more secure running in the cloud, so that we can fully isolate that and provide more guarantees on that. And yeah, the other one is generally local integrity enforcement. There are a lot of mechanisms that can be enabled in Linux, but also that just need to be flipped and have good policies in place so that you don't accidentally lock out a user during the exam. The next step is non-TPM devices. Unfortunately, a TPM is the only root of trust we have in many, many systems. But of course, like for example, the new M2 Max out there, and we want also students to use their devices. And then the challenge is, first of all, how do we support our distribution on that? And second of all, do we have some kind of root of trust, or can we add some kind of root of trust so that we can extend to that? And also, if you are a university, we are currently collaborating already in Germany and in Switzerland with different universities. But if you're interested in digital exams in this kind of form, just get in touch. And also we had interest from high schools, but a high school doesn't normally have a cloud connection. So we also are working currently with a MSP to provide a SaaS offering so that they can try it out. Yeah, so you can find more about the project on that link. And otherwise, I'm open now for questions. probably. Yep.
Sorry, I'm kind of short. So for the exams that were not accepted, what were examples of problems that arised which made them not accepted? Was it related to the remote attestation, or was it like other factors?
In what sense not accepted? So
Can you go back to the slide that with the smiley face?
Yeah.
Yeah, so you mentioned it was a high accepted rate.
Okay.
So what about the ones that were not accepted?
So it just depends on if it runs on your own hardware. So we also have like a big pool of like replacement devices in that sense. And also it depends if their use case was fully covered, and then, but generally there was not a big, oh no, we don't want to use it. It's more like we provide infrastructure to do exams, and in some cases there was also the expectation that we provide like the pedagogical and didactics track for that, and that we don't do. So there was sometimes then that, but generally the acceptance was not related to the remote attestation part at all. It was just, yeah, implementation.
Okay. Sounds good. Thank you.
So this is actually a really interesting concrete use case for keylime, which is great to see. I had a question kind of around bridging the gap between, in your diagram, you had keylime kind of in the learn stick layer, but then it's using the TPM, the hardware from the student. So like how does it kind of use the student's hardware? Are there any like how invasive is that? Are there any privacy issues around that? Are there like certain things the student has to do? Like if you don't have secure boot enabled on your system for your own reasons, like how does that affect the...
Yeah, so we have an onboarding process for devices. So the student brings their device because those kind of exams, we write them not like cold start, the student comes first with their device to the lecture hall, but there's normally an introductory session, and then the devices can be onboarded. For those familiar with TPMs, we chain the identity back to the EK certificate. And of course, there you could argue some privacy concerns, but that is the only one, because we need to have secure boot enabled to make that all work. But if they want, after the exam, they want to disable secure boot and enroll their own keys, they're welcome to do that. But during the exam, we want to have the secure boot chain like normally, and for the TPM, we use it as a device identity for the device to onboard that.
So the EK certificate from the TPM is the only thing from the student system that's entering this sphere. Okay.
And some the static PCR0 to have like CRTM measurements, because those are otherwise difficult to record. But yeah, the rest is complete. Our goal is to not touch anything on the student's device, which makes their life easier and also our lives, to be fair.
Thank you for that talk. So we'll take about a half an hour break now.